Hi. Yeah, okay. I always have to look in this direction towards the camera and read the chat here because my office layout is a bit suboptimal for streaming. Also, all you guys are going to be completely distracted by all the monitors and so on, and by the delay that you can see everywhere. Okay. Yeah, so first time streaming, we'll see how it goes. I prepared some stuff like with the camera and the microphone setup and so on. If something doesn't work, please let me know and then we'll fix it ad hoc. Okay, so it's been a while since I purchased a National Instruments USRP on eBay, like this box here, which is a software-defined radio. So it's a software-controlled receiver transmitter that you can use using GNU Radio or other software for doing general purpose RF, well, receiving and transmitting. And apparently, every single SDR I touch, I break. So it's been a bit of a sad story. I had a hack RF, well, that still works and I didn't need to fix it. I had a Blade RF that I had to fix twice because one clock distribution chip broke, and also a USB, the USB socket broke, which I had to change. So that still works, and then I got this thing, which is the best SDR I ever used in terms of like noise floor, and there is no DC peak, and the software just works. If you hit, like, for example, stop, and you don't want to get new RF samples, it just stops. It doesn't continue, it doesn't hang, you don't have to replug it like with other SDRs on the USB and all that kind of stuff. And so I actually used it for some time. And then I wanted to get a GPS disciplined oscillator for it. So this is the main board here. It's quite big. And there is a small socket here where you can plug in a GPS disciplined oscillator, which gives you a pretty accurate sampling clock of about 10 megahertz, or exactly 10 megahertz, which uses the GPS satellites as a timing reference. And then you can figure out how fast your local oscillator is ticking by waiting for a second, a pulse per second from the GPS satellites, if you want to say so. And then you can measure how far off your timer is, and then you can slowly start to change the frequency so that you get exactly 10 megahertz. It takes a while, it needs to warm up, and then it needs to be aligned so that you have a lock and it's exactly at 10 megahertz, and then you have a very, very stable and very accurate 10 megahertz clock. So National Instruments, the vendor of these things, they sell GPS disciplined oscillators, but they are pretty expensive. They cost like $1,000 for a small PCB that you just plug in here. So I looked on AliExpress, and of course Chinese people cloned these things. They didn't clone them directly, but they offered GPS disciplined oscillators for, I don't know, $100 or whatever. So I bought one. That thing arrived here, and I started plugging it in, and of course it did not work. So I started reverse engineering it, and I pulled it completely apart. I have, I can show you somewhere. Oh no, let's use this one. What this looks like. Yep. What? Yeah, these ones here. They are a small PCB sandwich with an oven-controlled oscillator in the top. This is the 10 megahertz reference, and then there is a bunch of circuitry below there on the board that controls, like with the GPS module and a small PIC and so on. So this didn't really work, and I completely pulled it apart, and I also reverse engineered it. And this thing is based on an open source GPS disciplined oscillator by some Canadian ham radio operator. And I have the complete source code. I drew a schematic and all that kind of stuff. And I found a bug in this thing. The bug is that the PIC that controls all of this runs at 5 volts, and the GPS GPS module runs at 3.3 volts. And it seems that the voltage levels aren't good enough for the PIC to recognize the 3.3 volt signal as a high state. It should, according to the datasheet, but maybe, I don't know, it's a fake PIC if there is something like that on there. I don't know. When I debugged it, it was weird. If I separated the two PCB halves and I put wires in between, it started to work. If I put them directly on top of each other, they didn't work. And then I raised the supply voltage by just 0.1 volt, and the thing started to work, even if the PCBs were on top of each other. So that was quite weird. And then I wondered why it wouldn't work on the USRP, and I measured the voltage on the header here, the supply voltage, and where 3.3 volts should be, my multimeter showed me 3 volts. And I'm like, that's weird. But that would explain why the GPS diode didn't work properly in this USRP. So I started measuring, and everywhere I measured, the voltage was too low. And I couldn't explain why, and I took it apart and I looked at the bottom of the PCB and I saw corrosion everywhere. So since I bought the thing used on eBay, I don't know where it's been used before. So I cleaned everything up very thoroughly, all the corrosion is gone, everything looks fine now. I plugged it back in, I measured again, and it was still 3 volts, and I couldn't explain why. So I checked the schematics, and the schematics told me that there is this 3.3 volt regulator, and this regulator is fed by another regulator that is supposed to produce 3.8 volts. And if that 3.8 volts regulator is too low, then all the downstream regulators, if they don't have enough operating margin, then they're going to be too low as well. So I checked the 3.8 volt reference, the supply for these other downstream regulators, and they are, and my meter showed 3.5 volts, which would explain, if you don't have enough headroom, that maybe the supply voltage would drop on the downstream regulator, so to 3.1 volts or 3 volts even. So that was weird. And then I wanted to measure the feedback voltage. The way this works, I have the schematic open here. There is a power tree somewhere. Pro streamer, okay, yeah. There is a power distribution here. So this is the whole power distribution of the complete board, and it has a lot of voltages because an FPGA usually uses a lot of different voltages. It needs core voltages and I/O voltages and so on. So you can see that 12 volt is supplied from an external supply, and then it goes in all kinds of regulators, like a 1 volt regulator for the FPGA core, a 1.2 regulator for whatever, 1.8 volt regulator, and so on. And here's the 3.8 volt regulator. And this 3.8 volt regulator supplies all the other regulators here, these linear regulators, although that's, are they really linear regulators? I'm not even sure, I think so. So here is some FPGA I/O voltage for I/O pins. Here is 3.3 volts supply for some voltage controlled oscillators, I think. Here's more clocking stuff. Here's this 3.3 volt supply for the GPS diode that I measured that was too low. And yeah, so this 3.8 volt regulator here is on page 21. Page 21 is here. It's this regulator here. And the way this works is 12 volt goes on here. And that is not even, that is a switching regulator. And the way this works is this 12 volt is switched through with a MOSFET, like a switch that opens and closes, and is fed through to pH2 and pH1. And while the switch is closed, if you will, this inductor is charged, and then in the next cycle it is discharged over an internal diode in this regulator into these caps here, one of these caps. And depending on the duty cycle, like how long do you close the switch so that the 12 volts is fed into this inductor here, and how much current you pull out of this system, you can get a voltage here that you want. And the trick how you set the voltage is that you feed it back into the regulator, and this works by taking the voltage here from the right side and dividing it down using a resistive divider and feeding it back into this V-sense pin. And according to the datasheet of this thing, V-sense should be 0.8 volts. So if the regulator senses 0.8 volts here, it knows, okay, I am completely in my operating region. I can keep the duty cycle of like closing and opening this switch here to set the voltage on the output just like it is now, and don't need to change anything. If this voltage here drops, because you pull out more current out of this cap here, then the regulator would sense a drop in V-sense, and then it would open up the regulator further and let more charge, more electrons through to this side, and then charge the inductor, and through the inductor the cap, and so on. And what I wanted to do is I wanted to measure V-sense, because if the voltage here is too low, it might be that V-sense is too low in the first place, or too high, because I suspected these regulators to be these resistors to be broken because of the corrosion that I found beforehand. So I wanted to measure the voltage there. Problem was that my multimeter that I'm always using, this thing, was set to resistive mode. And what happens if you set it to this resistive mode is that it puts out a voltage on the positive and the negative terminal, because it needs to put out a voltage so that it can measure the resistance or a current or whatever. I don't know which way around they do this with this particular meter. Point is, I fed a voltage or ground or a negative voltage, I don't know, into this V-sense pin, which I think led to this 3.8 volt regulator opening up completely and feeding the 12 volt through the inductor into all the downstream regulators. The moment I realized my mistake, I already smelled and saw magic smoke coming out from somewhere on the PCB. I wasn't really able to track down where that happened. And if we look at the schematics again, god damn it. If we look at the schematics again, then all of these regulators here got 12 volts, most likely. So what I then did is I checked if really something broke. I plugged everything in, and yeah, it didn't work anymore. So that was obvious because the magic smoke escaped. And so what happened was that this regulator below here, this 1.8 volt regulator, blew up. I checked all of the other regulators. I looked at the data sheets. If we look at, for example, page 23 here, we can see two regulators here. And it's a TPS 7A47, for example. And if I Google for that, what was that? TPS 7A47. Yeah. Then we can see here that it has an input voltage range of 3 volts to 36 volts. So if that thing got 12 volt, then it's fine, because it's perfectly capable of handling that. Even if there is a sharp transient in input voltage, the regulating loop should be fast enough so that no 12 volts got to the other side. So even if, especially if it's capable of handling like up to 36 volts. So that's fine. And I went through all the regulators and I checked all of them. All of these are capable of handling that. For one, the maximum voltage, like the maximum recommended voltage was like 10 volts or something. The absolute maximum ratings, after which it starts to like severely break, was at 13 volts. So it barely managed, but it should have managed, according to the data sheet. Except this one, and this is the most expensive regulator that could have failed, because this one is responsible for generating VCC MGT1V8. And that's on page 27. So page 27, 26, 27. It's this one here. It gets VCC 3V8 raw, and it spits out VCC MGT1V8. And if we look it up, it's a TPS 79318. TPS 73918? No. 79318. 79318. And this is going to be most likely a family, because the 18 is the output voltage. Yeah. And this one only, it doesn't say this here. If we scroll to the absolute maximum ratings, the maximum input voltage is 6 volts. So if I fed 12 volt into it, then this is the chip that blew up. And the way I found it was that I just took the PCB and I smelled where it smelled burnt. And this was the exact chip that blew up. So I removed that chip and I started to pray that maybe only this chip blew up. So the chip is right next to these two regulators here. Oh, you can't see. I'll show a close-up later as in proper setup. Yeah, I prayed that only the regulator blew up and it failed open, and that it did not really push the 12 volts downstream as well. But apparently it did. Because what even is this voltage for? So VCC MGT1V8 that apparently the 12 volt got fed into as well through this regulator goes right into this FPGA. So here is a bunch of voltage rails for the FPGA. U23 is one of the blocks of the FPGA. There are multiple of these because it's like there's like 900 pins. And this is the ground connections and supply voltages for things they call MGT, multi-gigabit transceivers. And this is the most expensive part of the FPGA, which are these transceivers that you can use for high-speed buses like 10 gigabit Ethernet, PCI Express, SATA, whatever else is there. They are very flexible transceivers that contain a bunch of blocks in hardware for clock recovery, for 8-bit, 10-bit decoding, all that kind of physical layer stuff that you have with high-speed protocols nowadays like SATA or PCI Express and so on. And you have several supply rails here, like a 1 volt supply, a 1.2 volt supply on the top here, and a 1.8 volt supply. And I looked it up what this rail specifically is for, this MGT VCC aux thing, and this is for a PLL that generates clocks for these multi-gigabit transceivers. And if I send 12 volt in this 1.8 volt pin, then I definitely fried something in this FPGA. Now I had hopes that these bypass capacitors here that are supposed to even out spikes in the consumption, in the power consumption of the FPGA, that these blew up because only 2 of them are rated for 25 volts. One of them is rated for 10 volts, another one is rated for 4 volts. And I hope that one of these failed short and maybe took all the energy and blew up and failed shorted maybe, so that I had a direct short to ground, so that all the energy went right through the FPGA from this regulator into ground and nothing in the FPGA broke. So I removed all of these from the PCB, and nope, there is still a short. So what I did to determine if there is a short actually, so after I recognized that I did a mistake, I tried it out as I said, and it didn't work. And then I found the broken regulator. So I removed the regulator and I soldered a small wire to it, and I put the wire outside onto my lab power supply. and I supplied 1.8 volt into it after turning the thing on. And according to the Xilinx FPGA datasheet, this pin is supposed to take in 200 milliamps. I turned it on and it immediately went into current limiting, which told me that there is a direct path to ground. So it fed 200 millivolts in there, and the voltage immediately dropped. And because I didn't want to break anything else, I didn't raise the current limit, because it's not supposed to be that way. So yeah, so then I removed all the caps and I tested again, and it still went directly into current limiting, and I decided that that's most likely it for the FPGA. So yeah, dump mistake. I think that's the most expensive mistake while probing I ever made. There were others, but they weren't that severe. So yeah, then the saddest story is there wasn't even a fault in the supply, because the stupid multimeter was just out of calibration. I plugged it into my lab power supply, set it up for 3.3 volts, and it showed 3 volts. That means this thing was just out of calibration. There wasn't even a fault, and I hunted something that wasn't even there. And in the course, due to another stupid mistake, I fried this FPGA. Now, yesterday when I announced that I would stream this, 2 people on Twitch approached me, on Twitter approached me and asked me why I think that I need to change this FPGA, because that is a last resort, like very desperate measure, because this is a multi-layer board and it's a 900 pin chip, and there are a lot of parts on the back side and on the front side, and we need to be careful that we don't burn anything and so on. And they asked this rightfully so, but after like doing some more debugging today, I am certain that the FPGA is okay, except this one voltage input. Because what I did was, for example, you can configure the FPGA using JTAG, and I also tried that, and the FPGA answered. So it has voltages present, so that all the logic works, so they can configure it, and I can read out temperatures and so on. So it's all good. But there was no blinking on the LEDs, which it usually did. So today I checked the source code a bit more, and it made sense that there is no blinking, because you need to configure a bunch of registers so that a few of these LEDs start blinking, and usually that's done by host software over 10 or 1 gigabit Ethernet that I fried. But this thing also has a PCI Express interface, and I happen to have an adapter cable and an adapter card, but I just never tried it out. So I took another machine, I plugged in this adapter card, I plugged in the USRP, I installed the Windows drivers, and the thing showed up. And it configured the FPGA and everything, and it detected it the way it was supposed to do it. What I didn't try was actual RF, but all the clocks are there, the LEDs started to blink and everything. Now, what I suspect happened to this voltage input is, on this input, there is a Zener diode that is supposed to protect the voltage input from over voltage. It's ironic, but I think I killed one of these, because these are attached to the voltage rail and to ground, for example, for a normal input pin. I would guess that this, for power inputs, it's only a Zener diode that goes from the input to ground, reverse bias, so that if the voltage gets too high, hopefully a lot of the energy gets dissipated into the ground lane, and you have kind of a short over this diode. But I think the 12 volts were too much, and I burned out the diode inside of the FPGA so that it now failed shorted to ground. Because everything else works. It's just that these multi-gigabit transceivers are now broken, and the PCI interface works by talking over a parallel undocumented bus to a National Instruments ASIC that sits next to the FPGA and the PCI Express interface. So you could use this over PCI Express without like fixing it, like just the way it is right now. It's just never going to do Ethernet again, and that is like of almost no use to me, because the the PCI Express stuff is very, it's undocumented. You need special software. There are Linux drivers, but only for certain kernel versions and so on. It's essentially unusable. So yeah, I am hopefully going to repair that today. And for that, we need to replace the FPGA. The FPGA is very expensive. The DigiKey list price is at, I don't know, $1,700, which is batshit crazy. But I, of course, didn't pay that much amount of money. I checked AliExpress in China, and I bought an FPGA for $130 US, which still is a lot. I don't know if it's new or if it's refurbished, like ripped out of some device, but to be honest, I don't really care. As long as the thing works, it doesn't matter how many hours it has on the clock and how often it has been used, because I mean, it's not like it's a car that breaks down more and more by just using it more. It was shipped to me like this, vacuum sealed with silica gel into a hard plastic case with anti-static foam in there. I didn't open it yet, so I don't even know if there's even an FPGA in there. So we'll find out soon. The good thing is it's packed, it's vacuum sealed, and it's packed with silica gel to prevent it from accumulating moisture, because we're going to bake it at a pretty high temperature to get the solder balls molten. And if there is moisture trapped inside this thing, you can get an effect that is called popcorning, which blows up the chip internally. As the water evaporates, it's trying to find a path from the chip to the outside, and it's going to do so very rapidly, and it's going to destroy the chip. So hopefully this is moisture free enough. I didn't bake it because in an oven, because it arrived with silica gel. We'll see how it goes. Yeah. So for the whole thing, I bought a BGA reballing, the resoldering machine. Just put this here. Put the board to the side. So this is the reballing thing, or not the resoldering thing. And this machine is relatively simple. It has a bottom heater that I already modified because there was a glass plate here that was relatively thick, and I did some training runs with an old motherboard, and the bottom heater just didn't really do anything. So I ripped this out, and I have a smaller preheater that I used for other BGA rework in the past. And this one had this like metal mesh in the front, so I just bought some on Amazon, disassembled the thing, ripped out the stupid glass plate, and just replaced it with this mesh. This mesh really is only for like preventing things falling onto the heater and burning immediately, because the heater gets really hot. And then there is a heater on the top, which is also just a ceramic heater. And both of these heaters are controlled by these temperature controllers that have temperature curves in them that are supposed to heat the board evenly from the bottom and from the top. And I tried this on a small ITX motherboard, which arguably was smaller than this. Also, this board doesn't completely fit, but it's going to be good enough, I hope, because here isn't really anything. And even the mini ITX board was a bit larger than this. And it didn't warp or do anything else that we don't want, so I hope that's going to be okay. I mean, the thing is scrap anyway, so there is no way around this than just actually fixing this. So yeah, the temperature curves, there were a few preset. I tried playing around with them and trying to make them smoother and attached more temperature probes and so on. The only thing I did was make it worse. Make it work worse and burn actually plastic and so on, even though I completely taped everything that I didn't want to heat up. But the problem is it turned out that the preset temperature curves are pretty good. When I did a few test runs with these, everything worked fine. I could remove chips, I could put them back on without a problem. I didn't reball them because the reballing kit isn't here yet that I ordered, but hopefully we're going to put this on first try, so it should work. I think the problematic part isn't even putting the new chip on, but it's removing the current chip, because there is a lot of stuff that can go wrong, because I need to clean the pads with solder wick and so on, and if I rip off a pad from the PCB, then it's going to be game over, because the PCB is going to be scrap at this point. Okay, so yeah, this is the FPGA thing. Oh, I also have lights, by the way. Look at that. Yeah. Okay. There is also a small holder for the PCB that goes over it, like that. And then you can take the PCB and put this on there. I think I had it. Oh, it's the wrong way around. Is it? Yeah, I think so. Okay. Yeah, I set it up before. There are these pins that can go through the holes on the PCB, and then you can accurately place it wherever you need it to be. Unfortunately, my bench isn't too big, but we are going to make it work. I hope that I don't burn any of the plastic. If that's the case, it's not there are a few plastic connectors like this JTAG connector here and a few fan connectors. If I'm going to melt them, I'm just going to remove them afterwards, and I'm just going to replace them with new ones. So that's not that much of a big deal. I even have these connectors in my parts bin. Okay, so the way you usually do this is I have this Kapton tape and this aluminum foil tape that came with this soldering thing. This stuff is complete garbage because there is glue on the other underside, and if you, I mean, it shields very well from the infrared the heaters emit because it's like aluminum foil, but the glue on the bottom side becomes a fluid, and it makes a complete mess on the PCB. So what I'm going to do is I'm going to first lay down a layer of Kapton, and then, just to be 100% sure, I'm going to put this on the top, so that the glue only makes a mess on the Kapton, and we can just pull it off afterwards and then have a relatively clean PCB. Yeah. Oh yeah, and I wanted to remove, I already removed everything from the PCB that I can remove. These things are press fitted on the PCB, so I can't remove them. This is the PCIe connector. This is screwed on. I still wanted to remove that because that is a giant heatsink, because it's like a full metal thing, and this is going to pull out all the energy we're going to put in from the bottom and from the top into the PCB to get it preheated, and that would not be good. And yeah, it's the first time that I'm actually soldering such a big chip. I did a bunch of smaller things. For example, when I fixed the Blade RF, it has a small USB microcontroller with 121 balls, so it's a 11 by 11 grid. I first thought that this one was broken because when you plugged it in, it didn't enumerate anymore, but the reason for that was that it didn't get a clock because this clock distributor I mentioned was broken. And so, because I suspected it to be broken, I I tried to replace it, and I replaced it multiple times, and I even reballed it, and the thing works. So I did this with just plain hot air and my other preheater because the board was smaller, and that worked fine. I also multiple times soldered DDR3 RAM because I reverse engineered an oscilloscope. That's on from Xilinx, where people are now building open source oscilloscope stuff with, by the way, now. And to get the DDR memory pinouts, I needed to pull off the chips and probe around. So I just desoldered the chips and I resoldered them afterwards. And the thing just worked fine first try. So this board, I don't know how many layers it has, but it has a lot of layers. But yeah, I think there is really no way around than actually trying it. Yeah, okay, now comes the boring part. I'm going to tape the thing up. I mean, let me plug it in and see if it's actually, if everything goes dark in a second, then the RCD or something else. Oh no, it works. Okay, so Chinese quality. I actually opened the thing up and I had to fix a bunch of wiring inside because otherwise it didn't really look too good. But now it should be safe. Yeah, so there's not much to do except taping everything up. Now the process is going to work as follows. I'm going to tape everything up so to prevent everything around the chip in question from the heat, because we really want to only heat that specific area of the board. From the bottom we are going to heat everything because the heat is not as concentrated, and it's a good thing to heat the board evenly so that there are no stresses inside of the board. And then we're going to let the heater do its thing, wait for it to finish, and then hopefully with some tweezers we can pull off the chip. This is going to be the hairy part, one of the hairy parts, because I have a problem. I only have tweezers. Every time you see people pulling off these FPGA chips, they're using something like a vacuum holder thingy, and I just today realized that I don't have one of these things. So we're going to be grabbing these things with tweezers, and hopefully I can pull it off. Unfortunately, there are a bunch of passives around this. The big caps are not I'm not concerned about the big caps around them, around here, but the smaller, what is that, 0201 resistors or whatever. And because I'm smart, I already measured them and drew a little schematic, well, board layout, which resistor goes where in case I need to repopulate them. We'll see. Oh yeah, that's the temperature sensor that we're going to need. So after I pulled off the chip, we are immediately going to clean up the pads as long as the board is still somewhat hot. For that I'm going to use a regular soldering iron and like this, and some solder wick very carefully, and if I make a mistake there is a high chance that I'm going to rip off a pad from the boards. If that happens, the only thing we can do is pray that it was a non-connected pad that's not being used, or that it's a redundant pad, like ground or some other voltage rail that we have multiple times. So it's not that important that one of them is missing. It's not great, but it's also it could still work. If it's another pad and it's in the middle of the array, there's no chance of repairing that. Like, at least not easily. If there is one on the outside, Maybe you can try and put a wire under there before resoldering the FPGA, but that's also, I mean, I'm not sure if I'm skilled enough for that, because I don't think you're going to get this right the first time. So, check on the so somebody has problems with streaming 1080p. Is this okay for, like, does somebody else experience the same issues, or is it fine for everybody else? Because I see 0 dropped frames. And because I'm not a Twitch partner, you unfortunately have to watch in 1080p, because there is no recoding support for, like, normal people. That are not Twitch affiliates. Or no, Twitch partners. Even affiliates don't get that, I think. Okay. Okay. Shit. More Kapton. Kapton is good. Now, how likely is it that I'm going to succeed? I'm really torn between it's going to be easy and it's going to be a complete disaster, because I have some experience doing BGA rework, but as I said, I never did it on such a large scale. And on the other hand, you see a lot of people on YouTube and in Chinese backyards, like very casually replacing Xbox GPUs or chips on iPhones or whatever. Of course, they're not doing this for the first time, but I don't either. So, yeah, I don't know. The process is, of course, not going to be as controlled as it's done as the manufacturer says it should be done according to the datasheet or according to some standardized soldering process. But come on, this is not a Mars rover or some medical device that needs to perform over years in harsh environments. So I don't think this is going to be a problem. If you're building a Mars rover, though, then you are supposed to have the money to do the proper soldering process. Yeah. Also, because I don't have one of these vacuum pulling things, I need to come at the FPGA with the tweezers at an angle, and I hope that I am going to be fast enough to pull it off before the solder bolts cool down again, and I rip off a pad. Because that actually happened to me while practicing. So one of these vacuum things would really be better, but I don't have it. So YOLO. Space rate is overrated. Yeah, I don't think it's overrated for space. Okay, so now we have a pretty thick layer of Kapton around it, and now I'm going to, just to be 100% sure, this aluminum foil thing on. Very liberally. Ah, shit. Yeah, this stuff is really a pain to work with. Anybody in chat who did FPGA rewalling, resoldering, reballing, whatever? I think we're going to make a mess on the PCB anyway, so we will need to clean it up afterwards, no matter what. But the glue is really, I don't know what's in there. As long as it's flux, it's okay. But if there is, I don't know, whatever stuff in there that is usually in glue, I don't want on the PCB, because I don't know if it's corrosive or whatever. Okay, then if nobody did BGA stuff, at least people who try to do SMD, like QFN or general stuff with hot air. Because actually I find SMD to be way easier by now and way nicer than through-hole, for example, because with hot air and a proper soldering iron, you just take your tweezers, put the thing down on the PCB, and then you tap it left, you tap it right, and it's on the PCB usually. With through-hole, you need to put the part through, bend over the legs, make sure the part doesn't fall out, turn the PCB around, solder it, remove the excess legs, all that kind of shit. Oh, fuck me. This stuff is just pure hate. There we go. Okay, one more and we should be good. Yeah, the fumes. I plan on not breathing them. That's it. So I have on my buying list, I have an actual fume extractor, but it's not that super cheap. And because I'm not doing this every day, I think opening the window is going to be good enough for now. I know it's not healthy at all, but I think I'm going to survive. I mean, if you are exposed to this stuff every day, then that's a different story. Yeah, also hopefully we're not going to trigger the smoke detector. I didn't in the past, so. Yeah. So much for just one more. I think 2 smaller ones and then we're really good. And then once we cleaned everything up, I think we're going to maybe have to redo all of that for the reattachment. So yeah, that's the boring part, but that's also one of the most important parts what I'm doing right now. Oh, come on. Okay. Temperature sensor. Now, these controllers are relatively simple. They only have a set time and a ramp, how fast they are supposed to heat up, and the target temperature and how long to hold that target temperature. So the curves are more or less standardized, and really, as I said, the standard curves that came with the controllers, or rather with the Windows software, not really with the controllers, they worked awesome. The bottom heater is going to heat the boards from the bottom to, I don't know, 100 degrees, 120 degrees Celsius. So nothing is going to melt on the bottom. Also, I think parts on the bottom are glued down because I had a really hard time removing, yeah, it looks good, removing these caps I talked about earlier that I hoped would have blown up. And I think they were glued down, and that is always a pain. So I hope nothing is going to fall off. I resoldered the caps on the bottom side already because that's really boring stuff, and it's essentially me like sitting like that over the desk and burning my hair while soldering. So I did this beforehand. I hope they don't fall off again. If so, we need to fix that, but I have a few spares. Okay. Tweezers. Second pair of tweezers, and once this thing is heated up enough, I think I am going somehow to take it on this side and on this side and just lift it up and put it on the side. I think that's a good plan. Yeah, maybe before I do this, we open this one and actually check if there's an actual FPGA in there. I'm not going to answer the phone now. Yeah, looks like an FPGA with like very very fine balls. It has a slightly different package, but it should be okay. So it is the right one, FFG 900, FFG 900. Yeah, that should be fine. I think. I hope. We'll see. Yeah. Okay. So current temperature is 21 degrees, that's fine. Let's see if I can give you a better picture of what I'm doing. That's maximum zoom. And yeah, I'm going to hit the fateful start button and we'll see what's going to happen. Let me check the program first. How did this work? $140 degrees, yeah, 170 degrees, then 225 degrees, and then we're going to stop at 230. I'm going to check with the Windows software and then and see if that is actually, if the thing saved the profile, because I'm not sure if it actually did. I just need to remember which of the VMs I had this thing in. So yeah, that looks okay. So it's going to, so the first thing it does is it's going to heat up over parameter set to 85 degrees over the course of 60 seconds, then to 140 degrees over 45 seconds, then to 170 degrees over 55 seconds, then to 225 degrees over 60 seconds, and then we are done. And once it reached the 225 degrees, I should be able to lift off the chip. Okay. Start. Yeah. So we're 34 degrees, 35, 36. So it's just a waiting game now. And I'm just going to closely watch what's happening, because in case something goes wrong. So it's 70 degrees. And it gets toasty. Once it reaches the 225 degrees, I'm going to tap the chip a bit and see if it's moving. And then once I'm sure it's actually moving, I can lift it off. Degrees, nothing out of the ordinary so far. The board doesn't warp or anything, which is good, I guess. $120, $125. $140. Still looks okay. It's now in the third phase where it's going to heat up to 170 degrees, and then afterwards it's going to ramp up to 225. Yeah. So we're at 170 now, and it should soon switch to the 225. Which is now. So 190, 91, 92. 93. So it shouldn't move yet. Yeah, it doesn't. 200. 210. 220. Not yet. Come on. That's pretty solid. Why? Shit. 25, 26, 27. Nope. And it turned off, and it's still on there. Shit. So the temperature was clearly not enough, but I don't know why. What kind of solder is this? Okay, well, shit. Oh yeah, the smoke is fine. I mean, this stuff is getting hot. Like with 225 degrees. But now I am pretty much stumped because I don't know what to do, to be honest. Ah, shit. So the only thing we can do is go up with the temperature. I mean, it is a massive heatsink, so maybe... Well... Then I guess we're going to raise the temperature. What does the datasheet actually say? There is a datasheet from Xilinx. Yeah. PB-free packages, that's it. Peak temperature, 230 to 245. So I guess we're going to up it to 245. PB-free. PB-free. Preheat temperature. Yeah, okay, we're doing that. So I guess we're going to go up to 245. Well, let's start. I really don't want to talk about how much this thing costs. But I mean, it's broken. It's essentially nothing worth anymore. So there's no way around of fixing that. Or there is no other way than fixing it. The thing is, I don't know for soldering it back on if I should use the same temperature curve, but I guess so. Now if this with 245 degrees doesn't melt, well, Yeah, okay, so the peak body temperature is 250 degrees for this FPGA package I have here. So yeah, if you try this with a heat gun, I don't think you stand a chance. If you only have the heat gun without preheating from the bottom, you would have to sink so much heat into it. I mean, I am sinking a lot of heat into it, and this thing doesn't move for whatever reason. So also, you're most likely going to destroy the multi-layer board with the heat gun, because you're not going to be able to heat it evenly, and you're going to introduce stress. Yeah, Kuchenblech, yeah, I wish. So we're at 140 degrees again. And it's starting to smoke again with the nice glue of that aluminum foil tape poisoning me. Yeah, actually, I hope that it would come off with these 225 degrees, because that always worked on my tests. And apparently, I was wrong. Okay. Yeah, now it's going to heat up to 245 degrees. I hope. Should have maybe increased the dwell time a bit more. The new chip comes pre-balled. Yeah, stack smashing. I think the temperature wasn't enough the first time, so I upped the temperature to 245 degrees, and I hope that it's going to come off now. The datasheet said that the peak body temperature for reflow is 250 degrees for this kind of package, so that should be fine. I mean, this thing is broken anyway. It's just about the new one. The chip is a Kintex 7 FPGA. It's a pretty big Xilinx FPGA with a lot of I/O pins, unfortunately, that I, as an idiot, broke. So I'm at 220. It still doesn't move. So if this thing really doesn't want to come loose, I don't know what to do. $240. And it turned off. I should have increased the dwell time. Well, shit. Now what, chat? Now what? Yeah, it's pretty solid on there. So either the board has so many layers that it doesn't get up to temperature inside of the board so that the solder doesn't melt, or the package has so much thermal mass that it just doesn't want to come off, because yeah, that is What do you mean by is it bottom soldered or pin soldered? It is balls. And the FPGA is the main chip of the board. It does all the data acquisition. It does Ethernet. It contains a little CPU that controls some registers and so on. So yeah, fuck. What now? I can increase the time to 90 seconds. And if that doesn't work, I'll stop. Because it's the third time that we're doing this now. And the regular hot air gun is not going to work because the I need to preheat the board from the bottom, and because the board is so thick and it has so many layers that oh shit, it has so many layers, yeah, like 16 or so, yeah, the probe is still in place. I'm sure I can see it. It's like taped to the right side, so it's fine. Otherwise, if the probe wouldn't be in place, the temperature controller would go absolutely crazy and heat it up even more and more and more and more and more. So, yeah. So I guess third time's the charm, yeah. That's why you don't do stuff like this on stream for the first time. Or they just used crazy solder, but I don't think. Yeah. I also thought about removing the heat spreader. What do you mean by desolder the holes? No, I'm not going to rip up the I'm not going to rip up the package, because that's going to destroy the PCB. Oh yeah, I really killed it with a multimeter. Why should I put it upside down? If it's not going to move the right way up, it's not going to move upside down. It's not like it's going to fall off. Yeah, I really killed it with a multimeter because I measured something on a voltage regulator in the wrong multimeter mode. I shorted something, and then the power regulator fed 12 volts into the FPGA. So that is how I killed it. Which is arguably a pretty dumb mistake, and I'm definitely not going to do it again. So okay. At least the board is still straight. That's something. Yeah, I know, temperature overlay and so on, but and you could read it out via USB, but I tested that, and the USB is relatively flaky. Also, the Chinese thing is weird. It, for example, has a USB device. It is a USB device, and it has a USB-A socket. So you need a weird cable and so on. And I tried it once, and then it in the middle of me soldering, the communication stopped working. The thing continues, but then every second the Windows software tries to pull the UART, it throws an error message, and you hear dring, dring, dring constantly. Yeah, the contacts are on the top layer, and there are solder balls that are between the chip and this top layer, and I need to melt the solder balls under the chip. It's not through hole or anything, and you can't really reach them from the bottom. Okay. Okay, 225. It should really move sooner or later. I don't know why it doesn't melt. Yeah, it doesn't really move. So we're 240 now, and it doesn't move. Well, I am preheating it already from the bottom, so it should be okay. Okay, so we're 240. Come on. Yeah, it switched off again. Ah, fuck. So yeah, it's not moving. Like, not at all. You can't really Google for something like that. So, what do? And I didn't expect that. I expected me to rip off a pad or anything else, but not getting off the chip. Hooray, we failed at the first step. Huh. Yeah. Yeah, I checked with another temperature probe before and it always worked fine. I mean, the probe is showing something and it makes sense. I mean, the way how this temperature rises is okay. But why doesn't it melt? I don't get it. It should really be melting at 245 degrees. I don't really want to go higher. Now the probe is next to the chip. And there is, so the probe is right next to the chip. So that should be fine. And it's not covered by anything. It's not covered by the aluminum foil. It's not covered by the Kapton. It's all fine. So that should be okay. Yeah, to be honest, the only thing I can do is raise the temperature even more, but yeah, the heatsink is most likely the problem. But I can't really probe under the chip. There's no way I can do that. So yes, this heat spreader on the top of the FPGA is most likely the problem. And the probe is too thick so that I can't really push it underneath. I mean, the chip is maybe 0.5 millimeters on the between the PCB and the chip is maybe 0.5 millimeters. And yeah, the board is plenty hot, so well, more time, more energy. I mean, not much else I can do. Problem is getting the thing back on again. And the tin foil is supposed to not conduct any heat. That's the idea. Because I really don't only want to heat the chip. Everything else I don't care about. Everything else is heated from the bottom, which is okay. But there is passives and other stuff around. And I don't think the passives melted. I think the board is just super thick. And there are just so many layers that you can't really heat it up. And that's also what I think the two people on Twitter yesterday meant when they said that with a board like this you're going to have a hard time. I can increase the temperature below, but it's not really super controllable because the temperature sensor is on top of the heater and not at the board, at the bottom board. I already set it to 210 degrees and the board is really hot. I mean, you can't touch it. Yeah. So yeah, raising the bottom temperature might be a good idea. And then I already set it to let it soak longer. So well, up to the next run, I guess. Yeah, that package is really a pain, and the board is really a pain to work with. But good tips, thank you. Remove the heatsink. Yeah. The temperature is Celsius, of course. I don't really want to remove the heatsink because removing the heatsink would involve me putting the pressure onto. Yeah, right. Yeah, and that's exactly what I try to avoid. Like plonk, just paste it into the chat because I fear that I rip off anything from the PCB because you need so much like, force to remove it. Yeah. Find anything large and connect to the plane and connect that to an iron. Yeah, that's not that easy. Also, the bottom heater is like a beast. It should be good enough to heat that up. I don't think I can do anything with an iron in this case. Yeah, planes are internal. How I'm going to heat it up? Okay, we're getting up to temperature again. Yeah. Okay, it's soaking now. And the thing just doesn't move at all. Fuck me. The thermocouple says 250 degrees now, because that's what I set it to. So it's really the maximum that you can according to the data sheet. And it's soaking for 120 seconds now. Yeah, and it doesn't move like at all. Yeah, nothing. Yeah, and it switched off. So that was 120 seconds and like nothing works. Oh, fuck. Flux, yeah, maybe. Can put on some flux, but I mean now it's cooling down already. Oh yeah, now there's flux under there. It's going to make everything smell like shit now. I am not going to be able to remove the heatsink. Also, if I remove the heatsink, then I'm going to have the same problem when putting the FPGA back on. So that is totally not going to help. And I fear if I torture the thing even more, the board is going to be fucked after this. So I'm also going to raise the bottom temperature even more. Yeah, there is, yeah, the next mounting hole is under the Kapton foil thing. There are a few for mounting a cooler next to the FPGA. Yeah, I think they are connected to ground. Okay, we try that soldering iron thing next. There's only going to be, I mean, using the soldering iron, you can heat the board, yes, but only one side of the FPGA. I mean, the FPGA is relatively big, so the other side is going to stay cool. Yeah. Yeah, that these LEDs have 900 balls on a 16-layer board, or 12. And then yes. Yeah, the amount of trolling, yeah. I just need to thank every 3 seconds somebody who just subscribed or gifted subs or whatever, followed. I don't know. Then it's a real Twitch stream. Yeah, heating the FPGA internally. That's what I intended to do in the first place, right? It wasn't even a mistake. I just wanted to, like, for the fun, change it. Fuck. Are there even channel points? I don't know. Maybe I should try and remove the heatsink, right? But I'm not going to, chat, just because you're telling me to. The dude is trolling. I mean, it is a valid strategy, but that doesn't really help, because I feel that you would need to put too much force on it to remove it. Yeah, streamers always have to listen to the chat. Yeah. Only if they sub. Oh, fuck this shit. Yeah, I don't know. Needs to be much more heat in there. Yeah, I'm going to do the iron trick next. I trust you there, because I know who you are. Not because you chat, just because I know who you are. And your name is Nurfudin Andi. I appreciate that. Oh! Yep. It's off. Okay. And it doesn't look like I ripped something off of the PCB or anything else. Easy first try. Okay. Now we're going to let it cool down a bit, because it's like absolutely flaming hot. And then I'm going to clean it up. And then we try to figure out how to get the new one back on. Okay, so this is the chip. You can see that? And yeah, of course it looks like a mess now from the underside. You would need to clean it up and reball it and everything, but the thing is broken anyway. I'm going to frame it or something. Okay, So we now need to clean up the remaining solder that is still on there. So let me get my big soldering tip. Some proper wick. Not this used shit. And I don't think you can see anything, right? Somewhat. And yeah, so I knocked off one resistor, but that's not a problem. I can easily resolder that afterwards. I'll just move it into place and hope that it reflows once we put on the new one. I'm going to take it off for now and keep it here so that I'm not going to lose it in the process of cleaning the pads. Okay, we're going to add some flux just for good measure. Yeah, rip off the pads now, yeah. Oh, do not try to rip off the pads. Okay, so yeah, it's a giant heatsink. Oh, what's my temperature at? A bit high. I'm taking off the bulk of the solder just by dragging the tip along the balls with some fresh solder. Okay, I think that's good. And now we're going to clean it properly. Come on. Bottom heater is not on, and I also cannot turn it on, unfortunately. Oh shit. I'm going to be a bit quiet now because I need to concentrate to not fuck this up. Oops. I fear the board is getting too cold. Okay, cleaning up 900 balls is shit. But 2/3 are done. Now I need to move in front of the camera. God, this takes ages. I really don't want to do this every day. Okay, I think we're good, and all the pads are still there as far as I can see. I'm going to clean it up with some alcohol, and then yeah, at least I can skip the reballing part. Yeah, until I fuck it up, and then I have to reball the new FPGA, and then I need to wait for the reballing kit to arrive first, which apparently is already in Germany, but okay. It's sticky. It's not super clean. Where's the wick? Where's the wick? Oh yeah, I have good tweezers. I mean, Chinese stuff, but it's good enough. The fuck? Oh, here. Come on, the board gets too cold, especially here. Seems to be a lot of ground and the wick keeps sticking, so I need to carefully heat it up again until I remove it. And that's why you don't brush the wick over the pads, because then you are going to rip pads off. Come on. No. It's still hot. Ah, shit. Okay, that's better, I think. Okay. Well, I would call that a success. Okay. Yeah, temperature probe is sticking up. So, chat, what's up? At least we get to skip through. Yeah, we already were there. Here's is the short still there? Yeah, good question. So I guess we're going to. Should I redo the whole isolation stuff and clean it up properly, or should I just keep it the way it is right now? Because I mean, the board is, well, it's not really hot anymore. Yeah, it's DMA Tech. It's essentially the same thing. It's not, in this case, it's not a MacBook, but another device. I can't zoom in further. That's the max I can give you. Everything you lose now, you need to put back in later. Wait, what do you mean? Temperature wise, it's cold anyway. It is completely cold. So I need to completely heat it up again. So the shorts. I mean, I can touch it, so it's cold. Okay, the shorts. Let's see. Yeah, it's gone. Yeah, that's ground. That's supposed to be there, but yeah, it's fine. So the short is gone. So it was the FPGA. At least something. So now what? Should I just leave it as is and try to resolder it? I mean, that's going to be a nightmare, just like removing it, but... Oh. Okay. So I'm going to put a bit of flux on and just spread it with my finger. Here's the FPGA. This is A1. Goes on like that. It has a different package, interestingly, like a different form of the heat spreader. There's like a little offset on this side here. Oh, it still has the cap. The resistor I desoldered, unfortunately. Okay. So, so luckily I checked before, and the solder mask is pretty much spot on if you just look straight down, and you can really nicely position the FPGA. The problem is I can't really see when it reflows. Yeah, that should be it. No, not quite. Yeah, I think that's... fuck. There's still a bump somewhere. Not sure. Shit. Okay, I think that's pretty much spot on. Well, I'm not going to eat the flux or eat the leaded solder, so that's fine. So why would I not use leaded solder as a non-company? It makes your life easier. I mean, look at this shit, how much energy I had to put in. Yeah, I'm going to solder the small resistor after the fact, I think. Or yeah, meh. Shit. Sticky tweezers. Okay, that's more or less on there. Okay, I guess then we'll heat it up again. It's the right orientation. Okay. I mean, it's on the pads now, so if it reflows, it's on there. I might even be able to use that as an indicator when stuff reflowed. Okay, now we need to heat it up like 5 times again in a row, right? The bros gods can go fuck themselves. Fucking gross stuff. Let it solder is so much easier than the lead. Yeah, lead is so much easier than the lead free. Okay. Yeah, the resistor will heat up faster, but last time I tried nudging the resistor when the FPGA wasn't reflowing and they didn't move as well. So it might not be that bad of an indicator, because the total thermal capacity that you need to overcome to get the board to this melting point of the solder will be relatively even, because there's so much ground around it that the heat will spread. You want to heat the board or the FPGA? Yeah. I'm curious if anything under the isolation survived, like the plastic stuff. I really hope I didn't fuck up the alignment. Oh, I wanted to check. I think I placed it on the board the right way around. I'm pretty sure. Yeah, it's correct. Well, as long as Xilinx didn't change the package markings, but yeah, heat is on. I'm just carefully looking at the FPGA and waiting for it to settle, but it's going to be so subtle that I might not be able to see it. Because I need to heat it like 3 times again, and I don't really want to nudge it, because if I nudge it too much, then I screw up the balls, and had that happen before. Yeah, the heat is, yeah. Beverly Hills Cop, or whatever. Careful with the DMCA. It starts to smoke, so the flux is boiling. And the question is, how do I see if it reflows or not? Yeah, sorry, I'm just really concentrating on trying to see if it settles on its balls. Yeah, I know that you're going to clip that. It might already have done this, but I might have missed it. Problem is, how do I know if it did it or not? Yeah, the board is pretty hot. So what you're watching is me trying to replace a huge chip on a board that I broke by accident. Okay. Yeah. I don't think it reflowed. And the problem I'm having right now is that the board is so thick and has so many layers that you need to put a lot of energy into it until the solder under the chip melts. And I am having a hard time seeing when this actually happens. And the black thing is not a microscope, the black thing is a heater. So the board is being heated from the bottom and the top, so that you get a more or less even heat distribution. But because the board is so thick, it takes a lot of energy to heat it up. So I'm just going to wing it and run it. How many times did we run it last time? 4 times? 5 times? So, meh. I mean, it's not like it's going to be super hot all the time. Instead, it's hopefully going to rise in temperature relatively gradually, so it's not going to die. Oh, it's currently at 190 degrees. It's always going through this cycle, obviously, that I set up. I should just remove the. I should just increase. I could just increase the dwell time, even more of the 250 degrees that I have at the end. That's 190 degree now. It's now in the. Usually, I think it would heat up to 140 now. So I thought I think I should just increase the dwell time of the last stage even more. Still at 180. Yeah, I think it's 180 even. So it is long. I think it's the same ramp. Yeah. I'm not sure if you can even set the ramp time and the dwell time. Oh, you can increase the rate of, yeah, the rate is currently 1. Whatever that means. Because now it's 175. It's the first two stages are essentially useless at this point because the board is at a constant 180 degrees due to the bottom heater, and the first two stages are getting the boards to the 180 degrees. Okay, now it's in stage 4. I think now it's going to heat up to 250 degrees and then stay there for a while. $180. $190. $200. $210. $220. $225. $230. $240. $249. $50. And now it's going to stay there. The question is if it already settled. I'm not going to see it again. Bottom temp is at 250 degrees, but at the direct heater, and there are a few centimeters between the heater and the board. So it was definitely not 250 degrees because the caps that I soldered with my lead-free solder are still on there. They would have fallen off by now. Okay, that was it. It switched off. Nope. So the resistor didn't solder. Yeah, I'm thinking about just blasting it with more heat. Fuck it. What was L? L was the... Yeah, I'm going to do it 3 more times. Hopefully the FPGA survives that. Yeah, I'm not going to increase the heat. 250 is fine. I'm just letting it run again. This time without like the whole... Because the board is hot. So I don't need this ramp up. I'm just going to give it more of the 250 now. Also, the thermocouple is not exactly on the PCB. It's floating a bit on over it, so it might not be that the temperature is accurate on the PCB, which isn't good, right? It's incredible that 45 people watch me staring at this soldering thing. I also can't see under the chip, so I can't look at the balls. Because the stupid insulation is blocking the view. Okay. So there was another 180 seconds. Let's see. Okay, the resistor is The resistor is soldered now. Should I nudge the FPGA? Yep, it's fixed. Easy, chat. Easy. So it's hopefully soldered. I'm going to let it cool down. And then I'm going to, as soon as I can touch it, I'm going to remove the installation and inspect the boards. And then see if the balls are shiny. Oh, fuck. Can you even clip stuff on like non-affiliates and non-things? There's going to be so many ball clips. I am going to look at the shiny balls. Before I can power it up, I need to resolder the voltage regulator, but that's easy. That's just a SOT 23-5 thing, like child's play. Yep, it's really on there. Cool. I hope that every ball melted and it really settled and not only half of them or something. Weird. Because I didn't see it coming down, but I always had a bad eye for stuff like that. Soldering is easy. Just get the right tools and a lot of flux. Like buy a JBC soldering iron and you're going to solder like God. It's really about a good iron. But the Valor is okay too, sure. I mean, I think the WD-1000 is the small one. Which one is that? Oh yeah, I mean, I think that's the same ballpark as the JBC stuff. I have the entry level JBC stuff, so that's good. And the cool about the JBC is that they have these cartridges and they are heating like right in the tip. So like this thick metal thing is the heating cartridge, and so you get the heat right where you need it. Yeah, toasty. Yeah, it's still too hot. I already thought about, for the lulz, buying broken GPUs and just reballing them. But even broken GPUs are too expensive. So it's absolutely crazy for what money broken GPUs are being sold. Also, all these kiddos breaking their GPUs are trying to scam you with like item descriptions which say, yeah, I don't know what happened to the thing. It suddenly started like not working anymore as soon as you launch a 3D application or whatever. I have absolutely no idea what could have happened to them. And then, I don't know, they played around with the voltages or whatever, or didn't cool it properly. So, nah. And then they're selling these things as partially working or partially broken. Yeah, great. If I can't use the GPU for 3D stuff, then it's not partially broken, it's complete garbage. But hey, the text mode renders, cool. Yeah, it's still toasty. Who's in chat? Let me see. Anybody know? Yeah, a bunch of people. Ha! How much battery do I have in the microphone thing? Yeah, enough. CPU garbage, yes. All these clips are going to haunt me for the rest of my life. It sucks. Or whoever you are. Too obvious. Ja, Grüße gehen raus an den CCC Ossendorf. Ja. It's still hot. Yeah, you cannot. Also, you cannot donate yet. I also don't have my own emojis. I need to become a professional streamer first, like Twitch partner and everything. I don't know what you even need for Twitch partners. I think you need 50 viewers, 50 or 70 sustained viewers over a week or something. But yeah, I mean, stuff like this is actual content that needs work instead of just playing a game. So I don't think I'll manage to do this more often than once a month, maybe. Yeah, it's still 100 degrees. According to the thermocouple. Maybe it helps if I put it down somewhere off the heat of the bottom heater. But I'm going to burn myself doing that. Yep. The plastic connectors even survived. Crazy. Shit. Yeah. Ugh. Yeet. Yeah, there are no parts on the... It's pretty dirty because burnt flux and everything, but yeah, I think that reflowed properly. I might have killed a cap, but meh. Ooh, 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 ooh. Ooh, ooh. Toasty. Okay, so I hope we don't need this anymore. And yeah, okay. Now, maybe, I don't know. We'll see once I turn it on, I guess. Close up. How do I can't really. I would not need to use the macro lens. I'm not sure if it's like on, to be honest. I don't know. It might not be completely soldered. I don't want to measure the resistance, to be honest, because I'm going to put voltage into the. I'm going to try it. I mean, linear regulator. If it's not on there fully and it doesn't work, then we're going to resolder it again, but then I'm going to need to pump up that much heat back into it again. Shit. Should have run it once more for good measure. Okay, solder. Yeah, shit. Of course, the last joint is a bridge. There, better. Okay, well then, I guess we are going to try it. Heat sink. Oh. And Ethernet. Power, and hopefully no smoke. But also no link. Yeah, so there is no link yet. Doesn't get overly warm. Yeah, okay, so it's most likely not soldered on properly because I have no link and the solder joints don't look super good, to be honest. They, I don't think they reflowed properly. How am I supposed to measure the power, the current? Yeah, it's not, I don't think it's reflowed. How am I supposed to measure the current? I can't, except like when I rip off everything in terms of regulators and so on. Ich habe keine Zange. Yeah, the bots on the top side don't really look good, to be honest. They don't look like reflowed. They partly yes, but not Not completely. Nee, ich habe sowas alles nicht da. Well, I guess I'm going to end the stream here, and then I'm going to resolder it a bunch of more times, I guess, after preparing it again, because that is definitely not fully reflowed. And then I hope that it's going to work. Because otherwise it's going to be very boring. I'm just going to put on Kapton again and all the other stuff. If I not already killed the FPGA, maybe. I don't know. Okay, well, I then let the stream running. Okay. Sorry for the headphones. Okay. Now this time I'm going to leave a space here so that I can watch the balls melt, hopefully. Although on this side they look okay. It's not hot air reflow, unfortunately. And now I don't have enough space to flip it around. Okay. Should I put on the what's it called? Aluminium foil thing again? Okay. Yay, blasty. Yeah. It's the second attempt already, so I already tried soldering the... So that's already the new FPGA that's hopefully not broken. Fingers crossed. But it doesn't seem to have reflown properly. So that's the second attempt. So I hope that it was that it would have been way easier to solder, because the tests that I did on like this motherboard, one pass with a proper temperature profile made everything melt in no time. That was super easy. This is complete crap. Okay. Okay. Now this time I'm going to add flux so that the bolts get shiny, hopefully. And then let's see how this works. It's going to be completely disgusting with the fumes. Okay. Let's go. Now the thing is, I can see the balls then. Deal with it. I need to see if it reflows or not. Whoa. And it's pretty hot in here because of all the preheating and shit. So we are at temperature now, but it definitely didn't reflow yet, because I can see that on the caps on the side. Just waiting for the smoke alarm to go off. Okay. It might have moved a bit, but I'm not sure. Yep, it's definitely reflowing. So when I nudge it, it's coming back. So I guess that's good. And there was a cap that was pushed on the side by the Kapton stuff, so we need to reattach that later. But yeah, so now it's definitely on, because I nudged it and it floated back into its position. So if I didn't kill it with excessive heat, then it should work. But I fear that I killed it. yeah, we need to wait until it cooled down again. Ah. Okay. Yeah. So the board is pretty dirty now from all the flux, but that shouldn't play a role. Also, that one cap that's missing, I don't think that's it's going to prevent it from working. And yeah, the boards look way better now. Yeah, I think that might work. Well, where's the power supply? Here. Okay, better, way better. Now, the brown marks are burnt flux. So here is a small LED next to this National Instruments ASIC. This ASIC is responsible for loading the bit stream into the FPGA. When I tried it before, that LED did not turn green. That means that the handshake between the ASIC and the FPGA for loading the configuration most likely didn't work. This time around, this LED turned green. So, if I give it some Ethernet now, come on. Link! The LED is green and there is traffic. Do you see that? Super nice. Okay, I'm going to turn it off before it overheats because there is no heatsink on there. Okay, now we're going to see if the thing shows up. Okay, let me switch. No, Pro Streamer, no, this. Okay. What even was the UHD USRP probe? Yeah, I think this should be it. So if I start it and wait for a link, then it should. Okay. Then we're going to, let's try the other one. Because the different network interfaces have different IP addresses. It's a bit dumb, but yeah, I know. I'm not going to, okay, so it doesn't find it for whatever reason. I know I should put the heatsink on. It's warm, but it's not overly warm. So there is a link, but I'm not finding the I'm not finding it on the network. Yep. 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 That's a repaired USRP, I would say. Yep. So the only thing I need to do is clean it up properly, put it back in the case, and plug the daughter boards in, and then we can test it properly. I just need to be careful to not transmit any like commercial broadcasting stations, FPGA and shit. Yeah. Are there people in chat actually wanting me to fail at this? I'm just too good to fail. To be honest, I had my doubts after it didn't reflow properly. I'm not talking about you, Florian. I'm talking about... Who was that? Yeah, I don't know. Yeah, nice. That's cool. Fucking easy, chat. First try. Oops, sorry for the loudness. I was too lazy to set up a compressor. I should do that for next time. Okay, so now we need to clean up the shit. I'm going to... Also, I need to resolder that cap that I removed. So let's do that first. That should be relatively easy, because it's still full of flux and shit. And I didn't even burn anything on the board, and I pumped it full with heat. It definitely wasn't healthy for any of the components. Okay. This is going to suck because there is a lot of thermal mass on there. Don't break it again, yeah, fuck you. Well, we are not done yet, so I don't know if it actually works. So Ethernet works, but I don't know if there are actual RF samples going to be received and transmitted. Oh, this is going to be shit. Okay. Yeah, that's the ground plane now. That takes a lot of heat. Like, I should have done this once when the board was still hot. It's not heating up properly. More juice. Oh, that sucks. Soldering anything on the ground plane on this thing is like an absolute nightmare. Fuck that cap. Yeah, I'll put that on later. It's not super important. Just one bypass cap. Should have enough capacity in other places. Okay, so toothbrush. And now some brushy. Don't worry, it's an anti-static toothbrush. I really don't know how I'm supposed to put that stupid cap back on without preheating the board again. This fucking thing is a thermal nightmare. Okay. So now we need to wait again until everything evaporated. Especially under the BGAs. Yeah, I forgot to floss every time. Yeah, there's flux residue all over the place, but yeah. Hot air, yeah, good idea. SMD TIG welding, yeah. The new FPGA looks way cooler than the old one. The hot air gun is some Chinese, however that's pronounced, int 852. So AOYUE int 852. The cheapest thing you can get, basically. Okay. Yes. Okay. There is still alcohol under the chip. And I guess it's not very pleasant for you if I blow into this thing while having the mic on. Sorry. Yeah, there's flux everywhere now. This thing should really get an ultrasonic bath or something like that, but I'd be scared to damage the crystals that are on here, because there are a few on here. But I mean, the flux is not going to do a lot of damage, I guess. I'm going to clean it a few times in the future and then get rid of it gradually. Yeah, not enough FPGA. So I hope this is the first and last time I have to do something like this. Okay, I guess let's put it in a case. The case is super nice, by the way. It's like complete metal and it's machined with filter things. I guess that's something you can expect if this thing costs 6,000 euros new. It's not what I paid for it. Not even close what I paid for it, just for the record. Limited edition. Yeah, it's now it's a limited edition. Now it's the Andy edition. So these are the RF daughter boards. These unfortunately only go to 2.2 gigahertz, so they're pretty much useless for anything ISM band in 2.4 gigahertz and Wi-Fi and so on, but nobody likes Wi-Fi anyway. Okay. Like that, like that. So I'm not going to screw anything down, I'm just going to put them on there to see if we are capable of receiving anything. So this is RX2 and this is RTX RX. Huh? Huh. RX2, TX, RX. Oh, the heatsink. Heatsink. Ethernets. Should maybe screw down the heatsink, but nah. It will survive, I hope. Okay. So that's all there. We have 2.4 gigahertz antennas on there, I think. So let's at least replace this one with something more tailored towards broadcasting stations. Yeah. Oh, I forgot to switch scenes. Yeah, okay, you're not going to find that one. That is okay. What was the IP address? It was the 252. Okay, let's turn it on. Check if system sound is muted, okay. I'm not sure. Oh, it's a different IP address. Yeah, okay. Shit. Okay. Okay, so it finds the front ends now. Oh, that's new. Ooh, yes! Easy chat. Easy. Okay, so right now it's only 10 mega samples, rookie numbers. Let's go to 40 mega samples. Yep. So that's a broadcasting, but I hope it doesn't, I mean, I'm running a Threadripper, so it should have enough bandwidth and everything for video encoding and 40 megahertz of RF bandwidth shenanigans. So, yep, it's back to life. So I successfully repaired my X310. That's pretty cool. Now I can break it again. Yep. So only thing left now is properly assemble it, make sure it doesn't short anywhere on the case. And I would guess the second RF port works as well. I don't know on the top of my head how to configure that using GQRX. So, yep. So how long did this take? 4 hours. Yeah, somebody hosted me for 12 minutes ago. Thank you. Cool. So yeah, I would call this a success. I mean, it was a tad bit boring. In between, where I just stared at melting balls. But yeah. So I think I need to come up with like more interesting stuff so that I can do this more often without breaking maybe according to DigiKey $1,700 FPGAs. I mean, yeah, that is what they really want for one of these FPGAs. It's crazy. I mean, this is one of the FPGAs we just soldered. And I think the one I have now is even better than the one that was on there before, because now I'm having an industrial temperature grade, and the one that was on there was a commercial temperature grade. So it's even an upgrade. Not that I need it, but yeah. I guess these prices are just so high that Xilinx essentially prevents people from, like normal people, from buying them in single quantities. But AliExpress has them for like $130. And it's pretty cool. I mean, the packaging was great. The shipment was great. I mean, it took 3 to 4 weeks. But yeah, pretty cool. It works. That's the most important thing. So yeah. So let's do the Twitch game. Are we going to raid someone? Raid? Oh shit. Is there somebody to raid on Twitch? Who are we going to raid? Is there some cool dude somewhere in how do I filter for category? I don't want to... Science and technology. There we go. Order by viewers, high to low. Full stack bootcamp. Russian, French. Yeah, I don't know. I'm not. I don't know who to host. I'm just going to end it. So yeah, thank you for watching, and maybe I'll do this again. Maybe we can use the USRP for something cool now that we repaired it. And I have to go. I don't have any more content. Sorry. So yeah, I guess that's it. See you around on the internet, hackerspaces, hopefully soon, wherever. And yeah, see you soon. Thank you. Bye.